You know, the electricity powering the lights in this theater was generated just moments ago. Because the way things stand today, electricity demand must be in constant balance with electricity supply. If in the time that it took me to walk out here on this stage, some tens of megawatts of wind power stopped pouring into the grid, the difference would have to be made up from other generators immediately. But coal plants, nuclear plants can't respond fast enough. A giant battery could. With a giant battery, we'd be able to address the problem of intermittency that prevents wind and solar from contributing to the grid in the same way that coal and gas and nuclear do today. You see, the battery is the key enabling device here. With it, we could draw electricity from the sun even when the sun doesn't shine. And that changes everything. Today I want to tell you about such a device. It's called the liquid metal battery. It's a new form of energy storage that I invented at MIT along with a team of my students and postdocs. Here's the first battery, a stack of coins, zinc, silver, separated by cardboard soaked in brine. This is the starting point for designing a battery. 2 electrodes, in this case metals of different composition, and an electrolyte, in this case salt dissolved in water. The science is that simple. The fact is that today there is simply no battery technology capable of meeting the demanding performance requirements of the grid, namely uncommonly high power, long service lifetime, and super low cost. This battery needs to be made out of earth-abundant elements. I say if you want to make something dirt cheap, make it out of dirt. Preferably dirt that's locally sourced. And we need to be able to build this thing using simple manufacturing techniques in factories that don't cost us a fortune. So I put low-density liquid metal at the top, put a high-density liquid metal at the bottom, and molten salt in between. Magnesium for the top layer and antimony for the bottom layer. To produce current, magnesium loses 2 electrons to become magnesium ion, which then migrates across the electrolyte, accepts 2 electrons from the antimony, and then mixes with it to form an alloy. The electrons go to work in the real world out here, powering our devices. Now, to charge the battery, we connect a source of electricity. Could be something like a wind farm. And then we reverse the current, and this forces magnesium to dealloy and return to the upper electrode, restoring the initial constitution of the battery. And the current passing between the electrodes generates enough heat to keep it at temperature. So this is the evolution of the liquid metal battery. We start here with our workhorse 1 watt-hour cell. I called it the shot glass. Along the way, we scaled up to the 20 watt-hour cell. I call it the hockey puck. And we got the same remarkable results. And then it was on to the saucer. That's 200 watt-hours. The technology was proving itself to be robust and scalable. But the pace wasn't fast enough for us. So a year and a half ago, David and I, along with another research staff member, formed a company to accelerate the rate of progress and the race to manufacture product. So today at LMBC, we're building cells 16 inches in diameter with a capacity of 1 kilowatt-hour, 1,000 times the capacity of that initial shot glass cell. We call that the pizza. And then we've got a 4 kilowatt-hour cell on the horizon. It's going to be 36 inches in diameter. We call that the bistro table, but it's not ready yet for prime time viewing. And one variant of the technology has us stacking these bistro tabletops into modules, aggregating the modules into a giant battery that fits into a 40-foot shipping container for placement in the field. And this has a nameplate capacity of 2 megawatt hours, 2 million watt hours. That's enough energy to meet the daily electrical needs of 200 American households. So here you have it, grid-level storage, silent, emissions-free, no moving parts, remotely controlled, designed to the market price point without subsidy.